Hello, welcome back. The title of this lesson is called The Area of a Triangle. This is part 1. Now, even though we call this lesson the area of a triangle, really what I mean is additional areas of a triangle. Because you all should have learned up to this point that a triangle can be found by taking 1/2 times the base of the triangle times the height of the triangle. I'm going to show you that here in just a second. We've been using that for a long time to find the area of any triangle we wish. But we have additional formulations for calculating the area when maybe I don't know the height of the triangle. Maybe I know the base, but I don't know the height, but maybe I know some angles inside. So I have several different, they look complex, but they're not so complex once I explain them to you, equations for the area of a triangle when maybe I'm given some angles and some sides. I even have the equation for the area of the triangle when I don't have any angles at all, just the lengths of the sides on the outside. So in the beginning, we're going to review the area of a triangle, show you where it comes from. I'm going to show you these additional equations for the area of a triangle, and then we're going to solve some problems, and I'm going to prove these to you. I'm going to prove these additional formulations for the area of a triangle as we go through the solution to our problem. So stick around to the end. I think you'll understand where everything comes from and how to use everything. So let's start from the very basics, right? From the very basics. We already know what the area of not a triangle, but a rectangle is. Here we have a rectangle here. We have 4 right angles here. And we have, let's call it the length and the width of this rectangle. Now, how do we find the area of a rectangular region like this? We call it the area of the rectangle is just the length times the width. So we call it length times the width, whatever it is. Now, 5 meters times 3 meters, we multiply. That's how many square units we have for the area of the object. So if we want to find the area of a triangle, what we do is we start with what we know. We start with this rectangular region like this, but instead of labeling this thing, the length or whatever, we can call this the base of this guy. And instead of the width, we can call this the height of this guy. So we just use different letters. And if we want to figure out not the area of this whole region, if we want to figure out the area of this triangular region right here, this triangle right here, how do we do it? Well, we already know that the area of the entire rectangle is length times width. So you can see that the area of this triangle, in this case it's a right triangle, it would be the area of the entire rectangle we have, but then cut in half. So the area of the triangular region that we have right here is 1/2 times the length times the width, or 1/2 to the base times the height. We're just relabeling what the things are called. So the reason it's 1/2 times the base times the height is because the base times the height is the area of the whole thing, but then we got to cut it in half because to make a triangle, we just slice it corner to corner. So it's 1/2 times the base times the height. Now, the way we've drawn this is for a right triangle, but it actually turns out that this equation for 1/2 times the base times the height works for any triangle at all. So for any triangle, right? Any triangle. We can draw some triangle. We can call it something like this, some weird triangle. It's not a right triangle. It's something like this, let's call it. And then we can say that the bottom here is what we could call the base of this thing. And the height is the vertical height from the very top of the triangle all the way down. In other words, the height here is not one of the lengths of the sides. The height is just the vertical distance from the top all the way down, where this thing forms a 90-degree angle straight into the bottom like this. And then we can say that the area of any triangle is 1/2 times the base times the height. Now, I'm not going to prove that to you here, but you can prove it very easily geometrically, because when you slice this thing in half, you basically have 2 different right triangles. We know how to find the formula of these. Of course, the base here would be smaller than B. The base here would be smaller than B. But when you work it all out and you add everything back together, you'll find out that the area of the whole thing works out to be the base of the triangle times the height of the triangle, which basically gives you kind of a rectangular region here. And we take half of that and we still get the area of the triangle. So we start with the area of a rectangle. Length times width, that's the area. We want to find the area of a right triangle, we just cut it in half. So it's 1/2 base times height. And it turns out that the same equation holds for any triangle. The only real issue is that the height of the triangle is always defined to be the vertical distance from the top all the way to the base. All right, so you might say, why did we continue? We already know how to find the area of any triangle at all. Well, let's continue down the road here. What if I don't have the height? What if I don't give you this number? Maybe I give you these other distances. Maybe I give you an angle and the base. And I don't give you any information about the height. So we have additional formulations for the area of a triangle. So here we are, random triangle, angle A, angle B, angle C, side A, side B, side C. Now what we're going to do is we're going to prove these in just a minute as we solve our problems. But for right now, I want you to just notice the pattern. Just ignore this. These are just different ways to compute the area of a triangle depending on what you are given. If I'm given two different sides of the triangle, like I have here, little b times little c, and the angle that's between them, then I can find the area of the triangle by saying 1/2 times these two numbers times the sine of the angle between them. Notice that b and c would be these two here, and sine A would be the angle between them. Notice for this formulation, 1/2 A times C, that would be if I was given these two sides, and then I would know the angle between them. Over here, A times B would be these two sides, and the angle C would be between them. So this formulation is most helpful if I have a side angle side problem, usually, because I have two sides and an included angle, two sides and an included angle, and so on. And if I calculate it using any one of these, then I'm going to get the exact same area. No matter how you work it, if you flip the triangle upside down and calculate it again, you're going to get the same area because the area doesn't change. But I might be given different pieces of information, side A or B or C or whatever, angle A, B, or C, and so I would pick one of these to use. Now I'm going to prove this to you in a second. I'm going to show you that it comes directly from what we just did, 1/2 base times height. It comes from that. So this is not a new magical thing I'm dropping on your head. It's something we're going to learn in just a second. Now, that's helpful if I have side angle side. But look at these formulations down here. The area is also equal to 1/2 times A squared. That's one side squared. But then the sine of angle B times the sine of angle C divided by the sine of angle A, right? And then I have it differently over here. Instead of A squared, I have B squared, and then I have A and C on the top and B on the bottom. So you see what's happening is whatever side I've squared here, I have the corresponding angle on the bottom. Here's a B, there's angle B. There's side C, there's angle C. And then the other angles are on the top. They're all sines here. All right. This is most useful if you have angle, angle, side, or angle, side, angle. You know, in these cases, I have two angles and a side, two angles and a side, two angles and a single side, two angles and a single side, two angles and a single side. So depending on what you are given, then it's going to be easier to use this instead of something else. But again, I'm going to show you in a minute where these come from. They come from 1/2 times base times height. So you're going to get the same, this is a shortcut way of calculating the area, but they come from what we've already learned over here. I'm going to show you how that happens in just a second. But if I'm given more angles and only one side, it's going to be easier to use one of these than in this case. And then we have the last situation on the board. This one has a special name. It's called Hero's formula. But actually in some books, you'll see it referred to as, with an N, Heron's formula. You'll see two different references, wherever you look. So you'll either see Hero's formula or Heron's formula, named after a person who discovered it. This one looks a little bit weird. It is S times S minus A, S minus B, S minus C. Now A, B, and C are the lengths of the sides of the triangle. S is something new I've defined as essentially A plus B plus C, and then I divide by 2 or multiply by 1/2. So you see, this one is telling me I can find the area of any triangle if I only know side A, side B, and side C, but no angles at all. Because A and B and C go in here, and then over here, A, B, and C go in here along with S, but S is relating only to A, B, and C. So this one is very helpful for the side, side, side case when I don't have any angles at all. So again, I'm not going to prove the third one. The Hero's formula is a little bit more involved. I don't want to prove it. It's not particularly enlightening. But we're going to prove the first two sets here. You're going to know exactly where they come from. If you really want to know where this comes from, you can certainly look it up, but we're not going to prove it in this class. But big picture is, if you have a side, side, side situation, this only uses the sides of the triangles. You can find the area. If you have two angles and a side, then you can more easily use this one. If you have two sides and an angle, then this is the most useful thing. But don't forget that they basically all come from 1/2 base times height. So let's solve our first problem, and we're going to prove some of these along the way as we solve both of these problems. So I want you to find the area of a triangle if the following I give to you is true. B is equal to 32, C is equal to 27, and angle A is equal to 108 degrees. So I'm just giving you information. I'm giving you two sides and an angle. All right, two sides and an angle. Now you could just use the formulas. Of course you could do that. I'm giving you two sides and an angle. So two sides and an angle, two sides and an angle, two sides and an angle. So I could pick one of these and you could do it. Of course you could, but you don't know where it comes from. You can't use this readily because I only have this. Only have one angle. You require multiple angles to use these, so you really can't do that. But instead of just copying a formula, that's boring. Let's figure out where it comes from, and that's what we're going to do. So we're going to draw this guy here. Now this is a obtuse angle. So essentially, we're going to have a triangle that looks something like this. Here we go. It's not exact, but it's going to look something like this because this angle I'm calling angle A, and that's 108 degrees. It's bigger than 90 degrees. All right. And if this is side A, or angle A, this one we'll call angle B. This one we'll call angle C. And then over here we have side A, and then here we'll have, let me switch colors, side C, but C is given as 27. And opposite angle B over here is side B, which is 32. So notice that I have a side angle side situation. And I told you that this was going to be helpful, this formulation for side angle side. So let's go over here and figure this out. Let's say that I never gave you these equations, these other little guys over here, and I just asked you, find the area of this triangle, right? Well, what would you do? You would write down 1/2 base times height, right? And so that's what you would write down. You would say, well, the area of any triangle is 1/2 times the base times the height. Whoops, got to put a B here. Base times the height. Now the base is labeled as side C, but we know it's 27 units long, so that's actually pretty easy. But what would be the height? In other words, if we were going to do this, we would calculate it as 1/2 times the base. The base of this triangle is going to be, let's call it side C. We'll put the numbers in later. Times side C times the height of this thing. But what is the height? Well, you got to look back to your idea here. When we drew our original triangle, we said the height of the triangle is defined to be from the tippy top of the triangle all the way down perpendicular to the base. But in our situation, the height is going to be from the tippy top right here all the way down perpendicular to the base. So this is a 90-degree angle. So this is the height right here. So it's not even really inside, like, you know, you wouldn't draw anything like this. It has to go from the top all the way down, and it's perpendicular to the bottom like this, right? So how can we get h from trigonometry or from math here? The side A, or the length h, is going to be the vertical projection of this guy right here. You can imagine this being the side of a triangle, the hypotenuse of a triangle, so to speak. And this is the included angle. I mean, if it were over here, it would be easy. It would be drawn the way it's always drawn here. But the fact that it's an obtuse angle doesn't change anything. It's going to be the side B times the sine of angle A. Remember, sine projects vertically, right? If I give you a triangle like this, and this is angle A, right? And I label the hypotenuse, even though I almost always label it C, but here I'm just going to put B here. Then if I'm going to call this the height of the triangle, I would say that the height is B times sine of A. Why? Because the sine of this angle is opposite over hypotenuse. So the sine of this angle is opposite over hypotenuse. So when you think about it, when you flip it around, the height must be whatever the hypotenuse is, multiplied by the sine of the angle that projects it in the y direction. Now, this is for an acute angle A. This is an obtuse angle A, but it doesn't change anything because when you take the sine of this angle, the sine always projects into the positive y-axis. If you imagine a y-axis right here, it's just going to project to the nearest y-axis, which is right here. So my bottom line is, when you take the sine of 108 degrees, it's still projecting and giving you that vertical component. So it's giving you that vertical extent up to the very top right here. So B times the sine of this angle is going to give me what I call h. B times the sine of the angle. Another way you can think about it is the sine of the angle is equal to opposite over hypotenuse. It's just that this hypotenuse is stretched backwards, so it looks a little different than it did here, but it's the same exact thing. Because sine always projects to the positive y-axis. It projects to the positive y-axis up there. So you're getting that vertical component. All right, enough talking about that. So what we have is the area of this guy is 1/2 times the base of this triangle times the height but the height is given as b times the sine of a, right? Now, I can flip around these because it's multiplication. I can call this 1/2 times b times c times sine of a. A is 1/2 BC sine of the angle A. Area, 1/2 BC sine of the angle A. Now you see where it comes from. The way you read this is you say, okay, this is 1/2 base times height. It's just that b times the sine of the angle, you call this angle A right here. B times the sine of the angle, b times the sine of this angle gives you the height. And the height times 1/2 times the base is c right here, that's the area of the triangle. Now the other formulations are doing exactly the same thing, but you're turning your head and you're looking at it from different ways. So for instance, this one is 1/2, the base in this case is going to be c, c, and a sine b, a times the sine of b is also giving you the height, because notice, if this is the angle here, if you multiply sine of b times a, you're also getting the exact same height, right? You're doing the same thing you were doing here. So the height, a sine b, times 1/2 of the base, that also gives you the area. You're doing the same thing here, except you're looking at the other angle over here. A, in that case, would be the base over here, and then, I'm sorry, b would be the base. This would be the base over here, and then a times the sine of c, a times the sine of c is giving you the projection, the height this way, like this. And so it's the same exact thing, it's just a different height and a different base. So that's why we have 3 different ones, looking at it from different angles, but it's always 1/2 base times height. So now we know where it comes from. Here's what we can do, and we'll get it from exactly what we would have done before. We find the height first, then we calculate the area. All right, so now we can finally solve this problem. So if we want to calculate the height of it, we could just plug it in here if we want to, but let's just do it the way we kind of did. Let's just calculate the height. B sine A. B is 32, sine of 108, right? So the height of this thing is, when you take sine of 108, multiply by 32, you're going to get 30.43. That makes sense, because if this is slanted back and it's 32, then the vertical height should be a little bit less than 32. It's 30.43 meters tall. And then the area is 1/2 times the base times the height, which is 1/2 times the base, which is 27, times the height, 30.43. And then what you're going to get is 1/2 times 27 times 30.43, you'll get 410.8, which is very, very close to 411, just rounding up, square units. So if this thing was measured in meters, then it would be 411 square meters, for instance. But don't forget what you're doing. When you do 1/2 base times height, what you're doing is you're first finding the height, which is from trigonometry, b times the sine of this angle, and then you're calculating there. So plugging it into this and doing it by finding the height first is the same exact thing, because everything is multiplied together. All right, let's move along. We're going to do another problem, and in the course of that, or in the beginning of that, we're going to prove the other equation. So we proved this, and we showed by extension that these are all true. Now we want to show how these are true. Okay, the first thing I want to do, since we now know that this is true, is I'm going to write down the area of this guy is 1/2 a times b. Let's use this one, a times b times sine of c. This is the area, or one way of writing the area. We know that the area is 1/2 times a times b times sine of c. We verify that, we know that that's true. And then let's do the law of sines. The law of sines. And what do I mean by that? We can just write down the law of sines. Now, usually you write the law of sines as, well, let me just do it this way. We can write it as sine b over b is sine of a over a, like this. All right, the next thing I want to do is I want to solve this guy for b. Why? Because I'm going to end up putting it in here later. But for now, I know that the law of sines is always true for any triangle. Now I'm going to solve for b. How do I do that? Let me move b over here. So it'd be sine of b is equal to the sine of a over a multiplied by b. I just multiply left by b, so it cancels. Multiply right by b, there it is. So now, to solve for b, I'm going to multiply by the reciprocal. I'm going to multiply by a over sine a. So what am I going to get? is on the top over here, I'm going to have A times the sine of B over sine of A, and that's equal to B. How do I know that's true? To get rid of all this junk here, I'm going to multiply by A on the top, so it cancels. And I'm going to multiply by 1 over sine of A. So I'm going to multiply by A over sine A, and that's going to cancel. Multiply by A on the top over sine A. That's why it shows up in A on the top and sine A on the bottom. Now I have B. Now, why am I doing this? We know that the area of any triangle can be written as 1/2 A times B times sine of C. Why? Because we just showed that these are true, and this is one of the variations. Then we use the law of sines, which is true for any triangle. And now I'm going to take this value of B, and I'm going to stick it into here. So the area of the triangle is 1/2 times A times B times sine of C. But the area is 1/2 of A times B. But now I know B is this gigantic thing. So I'm going to put it in here as A times sine of B over sine of A times sine of C. You see what I'm doing here? Now what do you have? You have a 1/2. A times A gives you A squared. Then this is multiplied by, this is like sine C over 1, so we can multiply the numerators. And what we're going to get is sine of B, sine multiplied by sine of C, and then on the bottom, sine of A. This is what we set out to prove. 1/2 A squared sine B sine C over sine A. 1/2, let's see here, 1/2 A squared, yeah, 1/2 A squared sine B sine C over sine A. 1/2 A squared sine B sine C over sine, just double checking it's right. 1/2 A squared sine B sine C over sine A. 1/2 A squared sine B sine C over sine A. So that's that version of it, right? If you do the same thing for the other, choosing another one of these guys and doing the whole thing again, you're going to get these variations, which are all exactly the same thing, which are more useful when you have two angles and a side. Because now I only need one side for any of these variations, and I need two of these angles. But remember, if I have two of the angles, I can always find the third one. So even though I need all three angles, if I have two angles given, I can always find the third one in order to prove that. So how did we get it? We started with the area of a triangle. Again, it comes from 1/2 base times height. Then we incorporated the law of sines. All we did was write down the law of sines, solve for one of the sides, and stick it in there. And then out pops a version of the area that only requires one side and these angles. All right, so let's see how to use this. All right, what if I give you the following triangle? What if I give you the following triangle? Here is a very long and weird and skinny triangle, right? This guy is angle A, if I can write an angle symbol correctly. And here, A is equal to 2.2 meters. And this guy is 65 degrees, and this guy is 100 degrees, all right? Now I have angle, side, angle. So I'm given angle, side, angle. I'm not able to easily use these because I only have one angle for each of these, but I would need two sides. So I'm going to use one of these. And the version I'm going to use is the version I just wrote down. I'm going to use the area is 1/2 times A squared times sine B sine of C over sine of A. That's exactly what I wrote down here. Sine B sine C over sine A, and then you have the A squared like this. So the area is 1/2. Notice this is angle A and side A, and so it's 2.2 squared. And angle B, if this is A, then either one of these could be B or C. So you could label this B, and you could label this one C if you want to, like this. So what we could do is have up here, this will be the sine of 65 degrees. And then this is going to be the sine of angle C, which is 100, like this. And on the bottom, it has to be the angle opposite of the side I have here, which is angle A. But what is angle A? Well, I can easily find that. Angle A is 180 minus this 100-degree angle minus this 65-degree angle, right? And so when you take 180 minus 100 minus 65, you get 15 degrees. So angle A, 15 degrees, goes in right here. So the area is 1/2. 2.2 squared works out to be 4.84. right? On the top of this fraction, the sine of 65 degrees, you get 0.91. Sine of 100 degrees works out to 0.98. And then you have on the bottom of this fraction, sine of 15 degrees, which is 0.26. So if you take 0.91 times 0.98 and then divide by 0.26, take that result times 4.84 times 0.5 or 1/2, you will get 8.35. And since the units were in meters, this is squared meters. So here we applied the formula for a triangle where you have more angles than sides, and it's like angle side angle. We immediately calculate it. Now I like using these equations and formulas because they make it easy, but sometimes students, they just use them and don't know where they come from. But now you know they come from 1/2 base times height, and then we use the law of sines and the law of cosines. And now you can see how math builds because we prove the law of sines. We know it's true. We prove the law of cosines. We know it's true. We know 1/2 base times height, and now we combine it all together to make a formula that is easy to find the area of a triangle. Now, if we didn't know this, how would we do it? We would have 1/2 times the base, but then we would have to find the height from here all the way to here, and we would have to draw the angles, and it would involve a sine and so on, and you would get exactly the same answer if you did it this way or this way. That's the whole point of it. There's more than one way to get to the answer. So here we've covered the area of triangles. We started with the normal equation for the area of the triangle we all know, and we showed that there are multiple variations, but they all essentially come from 1/2 base times height. And then we have this other one we haven't used yet. We'll use it in the next lesson called Hero's formula. That one's good for side, side, side. So solve these, make sure you understand. Follow me on to the next lesson. We'll continue to build your skills.